So, not recording yet. So what? That's on her. She always gets pissed when she'll like leave like that, and then I'll start lecturing. When she comes back in, she's gonna get pissed. I'm gonna start lecturing them. All right, she'll catch them. Okay, so absorbing light, reflecting light. Let's go a little bit further into this. So within these things, which we call thylakoids, we have chlorophyll, pigment, right? And within the chlorophyll, you've got all these hydrogen atoms. So now I'm going back to this thing. I'm not going to do it for long, don't worry. So that's an atom of hydrogen. If you remember, it's got like a proton inside, an electron going around it, and so usually when these when these atoms get hit with sun, here's the sun shining its sun's always happy, shining its photons, like all the photons are coming down and shining on something. Usually what happens, like let's pretend this is your car, like the hood of your car. This electron's going around the hydrogen, and when the photons hit it, the electron's going to jump out of its orbit. It gets like, as it's going around, when the photons hit it, it starts like getting unstable, and then it jumps out of its orbit and it returns right back again. So it doesn't stay gone. It goes out, it comes right back, and then heat is given off. I could have sworn I have this in a slide. Maybe also some garbage. Oh yeah. Yeah, that's what that slide's trying to say. So the photon hits the hydrogen atoms, the electrons jump out of the orbit, and they return back. That's with everything else that's not plants. Plants can catch that electron. So the electron's going around, the sunlight hits it, it starts wobbling, and then it jumps out of its orbit. Before it can come back down, the plant catches it. So that's a source of energy. Most other things just get hot when the sun hits it. Like the street, like those wavy things when you look at the street far away. That's the sunlight hitting it, the photons hitting the street, and then the heat coming up. Because the electrons are just going right back to the atom. But plants know the electrons are going to get caught. That's the whole key behind, really, it's the key behind everything. Because since plants can do this, they can make sugar, and then other organisms can eat the sugar, and we can eat the plants, and we can eat animals that eat the plants. So it all kind of begins with this one simple act of catching this electron when it leaves the atom. It's the key to everything. And of course, the byproduct of this eventually is going to be the release of oxygen, but we'll get to that. So the electron jumps out of its orbit, it's caught, and we can use that electron now. With if you think back to cellular respiration, we had to eat food, and we had to go. You're good. We had to go through glycolysis and Krebs cycle, and that we had to go through that process to get the electrons. So this is going to be like a little bit easier. So let's look at light reactions. I got two slide versions of it. Why? That's my first version, but I've got like a different version. So within the thylakoids, you have these two different photosystems. This one seems to be easier to work with. Okay. Are you all freaked out, coughing like everyone's gonna run away? Are you? Do any of you guys freak out when you cough, like a normal cough, like everyone's gonna run away from you?
Yeah. I haven't get no weed. So
It's too hot.
I don't know.
I'll try to turn it down. I'm not gonna listen to it. In the thylakoid, you've got these two different systems. There's photosystem 2 and photosystem 1. It's backwards. Like, why is it 1 before 2? It's like the order that they discovered it. They just didn't feel like changing it. They discovered this one first, and then they realized that there's one before it. There's another photosystem that comes before it, and that's it. But we have other names for these, actually. I'll be on the next slide. So let me sum this up, what's going to happen. Here's the sun. Here's the sun. Tell me what I'm doing. I know it's because I'm old. I get that, but aside from that, what am I?
Try to pause it.
I paused it.
No, it didn't. It said, it don't say
Oh, I
freeze.
paused it. You saw me.
Yeah, look for the freeze word.
But you know that when I look at like my screen, I'm on a totally different slide now. Like when I pause it, it starts like my screen starts doing other things. Whatever. You know, what I should do is just spend half a day just master this thing. Probably does a lot of shit. There's like pens over there, and I could probably make like really good use out of it. Do you guys have any like instructors that use this, like use the pens and like interact with it? Or are they like me? They just, or do they not even turn it on?
I wouldn't know. I have not been in a class setting since last semester.
I should really use it. Either you really know how to like use whatever it is.
It's been about 10 years for me. So when I was in school, they didn't have that.
We used to have smart boards, like even in 2005, we had.
In high school, we had the Promethean board, but when I was in college, well, first time I was in college, they didn't have whatever that is.
It's people like us were resisting it. And the pens really get a long time. You have to like really get used to it. Like this thing probably will work, but it's like when you write, it comes below where you're writing. Yeah. See, I shouldn't even mess with it. I did it a few times, but can't get used to it. To be honest, I want the chalkboard. Like I don't even like using these pens. So same thing like this. Sunlight hits all the atoms in this photosystem. The electrons are going around. They get bounced out of their orbit. They never make it back. They get caught. So that's that lady up there. She catches the electron. Everything else is not autotroph or plant. This thing's going to come back down. Right, but it's caught. And then we're sending it down. If you remember from Monday, the electron transport chain, the same thing. Like, remember that thing about like we use the electrons to turn on these pumps, and you send all the H pluses to one side, and then they diffuse back over. That's what's going on here. So we can make ATP with that. Same idea. So this little mill is making ATP, and these electrons are going to roll into photosystem 1. Same thing. The sun hits it, they bounce up, but now he's going to keep those electrons. He's not going to make ATP with it. He's going to hold on to them. So he's putting them in the bucket. So we got two types of energy here. And you remember, like I told you, this thing, if it starts with NAD or FAD, they're electron carriers, right? So that's the bucket. Whenever you see NAD or FAD, they're carrying electrons around. So we got two types of energy. We've got ATP and we've got electrons. So the light reactions are making ATP and electrons. They're using the sun's energy. The photons coming down, that's a transfer of energy. That's going to make the electrons jump out of their orbit. 2 times, here and then here. But here's like a thing, okay, when the electrons get bounced out, like here's like a thing of hydrogen, right? With its electron, the electron bounces out of its orbit and it's caught, so it never goes back. Like here, okay, same, the hydrogen atom loses its electron, like he caught it, right? But here comes another one down this ramp. So we can replace the electrons here from the electrons coming down the ramp. The question is over here, electrons get bounced out, then like it's gone, right? So it went away. So like you got to replace these electrons, otherwise the plant's going to run out. So we're going to do that with water. As long as the plant has water, you can. So, water is H2O, so it's like 2 hydrogens and an oxygen, like H2O. So the plant will split the water molecule up, take the electron off of this, put it back here. Take the electron off of this one, put it back here. And this oxygen it's going to toss back out. It doesn't want oxygen. So the plant uses water. It takes the electrons off of water and gets rid of the oxygen. These it can use. This will come later, these protons. But anyway, where does the plant get electrons to replace these that are lost? It gets it from water. That's the answer. So let's go back and look at this other one. Not that it's going to make any sense. Photosystem 2, we call it also P680. Photosystem 1, we call it P700. It's like that's the wavelength of light that each of these photosystems like the best. It's like their favorite wavelength of light. Photosystem 2 is at 680. Photosystem 1 is at 700. Sunlight hits it. Electron jumps out. It goes down the electron transport chains. They've got it labeled. And then it rolls into photosystem 1. Now again, sunlight's hitting photosystem 1. The electron jumps out. This is not exactly right. It's going to be kept instead. As you see, like NAD, they're going to hold the electrons. So we've got 2 things out of this that we're going to take over to the dark reactions. We've got ATP, and we've got electrons. We're going to take both of those over to the stroma. These are light reactions. So these are all happening in the thylakoid. All of this. All this is in the thylakoid. The Calvin cycle, which otherwise are known as dark reactions, are happening in the stroma. So the whole purpose of the light reactions is to get the energy and bring both of these over to the Calvin cycle. So it's bring you to a Calvin cycle. Keep walking over there to switch slides. Before I get to the Calvin cycle, this is just showing you the same thing. You know, like in us, we do this in the mitochondria. Remember, you had all these pump all the H pluses to one side, then they come through, and that makes the ATP. Plants can do that in the chloroplast. Plants have mitochondria too, but as far as like photosynthesis, they're going to do that. They're going to run this same process in the thylakoid. So same idea, right? It looks very similar to the slide that we had last class. Turn on these pumps, pump all the H pluses, protons, to one side, then they're all going to flow through here, and that's the machine that puts the ADP and the P together. I mean, if you're going to take like a test, like a nursing school or GRE or something like that, they actually refer to this word right here, ATP synthase, right? Well, actually, let me ask you, what is ATP? What do you know about this, whatever it is? You recognize the words. What's the first part of it? ATP. What's this mean right here? As soon as you see that ending, that's going to tell you something.
Metaphanes, prophanes, metaphanes, prophanes, all that stuff.
Oh, yeah. Okay. Oh, wow. I didn't realize that. No, okay. Yeah, that's confusing. That word's actually phase. The end of that word is phase.
That's what I was trying to say.
Yeah, I get what you're saying. But that's not, this one is just about the ASE, the ending ASE. It's not like phase. So prophase, metaphase, like those aren't enzymes, right? But if a word ends with ASE, except for what you said, that word ends with phase. This word ends with just ASE, and that tells you it's an enzyme. This word synth, whenever you see that in a word, it means to make, synthesize. So it's an enzyme that makes ATP. So technically, all these protons going through here is activating this enzyme. This enzyme is going to put these two together. Just in case you see that on a test, just remember that word ATP synthase. That's the enzyme that makes ATP. I keep referring to a machine, like a mill, like a water wheel or something. The real answer is that it's ATP synthase. But in either case, you have to have electrons to turn these pumps on. With us, we pick the electrons off of our food. With plants, they're taking it from water. They're using the sunlight to help them do that. So it's just the only difference between plants and us is like where we're getting our electrons. But as far as making ATP, we go through like a similar process. Really, I'm about I should do just stick back here. This is a Calvin cycle. This is the dark reactions. I'm not gonna do it because I think it's confusing. There's just a couple of things I want you to know about it, but it's really confusing because you're supposed to follow this through like 6 times. But anyway, this kind of looks like the Krebs cycle. But the Krebs cycle, I was telling you, was like a molecule shredder, right? It shreds up molecules and picks the electrons out. This is the opposite. This is going around, but it's building something. It's not ripping up anything. It's doing the opposite. So this thing keeps going around, and you keep dropping carbon dioxide into it. So the plant's taking carbon dioxide from the air and it's dropping it into this thing that's going around. And as it's going around, the plant is taking carbon, take another one. And every time it takes 6 carbons, it's going to take the carbon and it's going to add some oxygens and hydrogens to it and mess around with it. And every time this thing goes around 6 times, you end up with a molecule of glucose. What was glucose again? C something?
C6H12 O6.
So it's carbon, hydrogen, oxygen, right? So we always follow carbon when we want to talk about molecules. We look at the carbon, right? So it's going to take one carbon. So carbon dioxide's, CO2. So when we take one molecule of carbon dioxide out of the air, we've got a carbon, we've got 2 oxygens. We take another one, we've got another carbon, take another one. Some of the oxygens we're going to use to make the sugar, some of the oxygens we're going to have extra. And the extra oxygens, for the plant, you just get rid of it. Throw it back out into the air. So the plant's taking CO2 out of the air, and it's returning oxygen. It doesn't really want the oxygen, it wants the carbon. We're the opposite. We breathe in oxygen because we don't want carbon. We're trying to get rid of carbon. The plant's taking in the air because it wants carbon. So this thing goes around. For every 3 times it goes around, you end up with this molecule. I don't know if I paused this or not. G3P, glyceraldehyde 3-phosphate. G3P, which is like half of a glucose molecule. I don't know. However you want to say it. If it goes around 3 times, you end up with G3P. If it goes around 6 times, you end up with a molecule of glucose. There are a couple of words, just FYI, if you're going on to do biology stuff. One of them is this word, rubisco. Sounds like a cookie. Rubisco is the most common enzyme in the world. And I'm only telling it to you because I've seen it on these placement tests. Not placement tests, like the T's, and I don't know what nursing people are doing now. They change it every few years. But there's always questions like, you run into questions like this. And you're like, well, why is a question like this ending up on a test for nursing? I don't know. Don't make sense to me. But the 2 words you'll see are these 2. Rubisco is an enzyme that adds this to this. So this molecule called RUBP, ribulose biphosphate, is going to come around and it's going to pick up carbon dioxide. That's the enzyme that makes it happen. That's just FYI. I'm not going to ask you that on a test. What I want you to know from this is that this is the Calvin cycle. This is the dark reaction. Calvin cycle, also known as dark reactions. And I want you to know where it happens. I should write this on the board, huh?
Couldn't hurt.
Never hurts. Just a little afraid to. You know what? Yeah, I'll keep it up. Dark reactions. Also known as light independent. Dark reactions. Yes.
You said light independent?
Yeah. Yeah, they're called, the new thing to call them is light dependent and light independent. But I'm like, dark is 4 letters. Light independent is however many letters that is. Right. Stroma happens in the stroma. And what's the also known as, Calvin cycle, named after Melvin Calvin. Happens in the stroma. What's the purpose of it? Converts ATP and electrons to glucose. Because the plant wants to store some energy for like the winter or for whatever.
You said it drops carbon into, it drops carbon into the
carbon dioxide.
Okay, so it drops carbon into the Calvin cycle, then after 6 rotations, it makes glucose.
Yeah. So you just imagine something popping into this machine, and then out the other end, something's like coming out the other end. It's not like really what's happening. I just want you to like try to understand it. So you're dropping like these CO2 pellets into the machine, and once you drop like 6 CO2 things into the machine, a thing of sugar pops out the other end. You look at it like that way. Because if you follow this slide, it doesn't actually make any sense. It's like, well, these are 5 carbons, and then here's 1 carbon. I should have 6 here, but then I've got like 3 and like. At the end of the day, we just need to know what it does. So yeah, that's what it does. Converts ATP and electrons to glucose. And of course, the plant, like if it's corn, the leaves of the corn plant are making the glucose, and then it takes the glucose and stores it in the corn kernel as starch. So we could tell the whole story now. French fry. No, let's go further. I'm writing on the board. I'm moving my muscle. Why? Because that P that used to be part of ATP is touching my muscle. Why is it touching my muscle? Like, where did it come from? Like, okay, the P touches my muscle and puts the energy into it. Where was it before it was P? It's ATP. I've got a shitload of ATP floating around my body in my cells and stuff like that. How did I get the ATP? I had to put it together. So the electron transport chain, I put it together in that last step of respiration, the electron transport chain. So I created like this proton gradient. In other words, all those H pluses on one side. How did I create that? How did I get all those protons on one side, all those H pluses on one side in the mitochondria? The electrons turned on the pumps. But then I had to get the electrons from somewhere. What part was the part that harvests all the electrons? Krebs? Those electrons were on this molecule called acetyl-CoA, which used to be pyruvate, which used to be
Glucose?
Yep. Which used to be, in this case, I'm going to get my glucose from corn. So it used to be starch. Corn is starch. Because I ate it. I ate the starch, polysaccharide. I ate it, and then like my stomach and my intestines broke it up and turned it into blood sugar. So then the sugar that was in the corn is now in my blood. And then it goes into my cells. And I start to break it down once it's in the cells. And start doing all this with it. So now we look at the corn. course, they process it in the tortilla factory. That's what I had this morning. They processed it in the tortilla factory. But I mean, it's starch. It's starch from the corn. Where did the corn get the starch? Like before, it used to be starch in that kernel, in that yellow corn kernel. What was it? What did the leaves make? Don't be afraid to say it. Glucose. So it used to be glucose from the leaves. So this is like the end of the Calvin cycle. Before it was glucose, it was carbon dioxide. It was those two ingredients that we used to make, that the plant uses to make glucose. Where did we get the energy to do that? We got them from the light reactions. And originally the light reactions came from, like, how did we even get that? How do we get the energy to get the ATP and the electrons? You know, that thing where you have the construction workers and that lady caught the electron and put it down that ramp. Like, where was the original source of all this energy?
Photons?
From photons. And it probably goes further on both ends, but that's the limit of what we know in biology. It came from sunlight. Moving my muscles to write on the board came from sunlight. And all of this could be represented by one law that we didn't have on today's test. Oh yeah, you're right. What's another law?
First law.
Stop fucking up my feng shui of my lecture. Yeah, conservation of energy is correct. What's another one?
First law of thermodynamics.
First law of thermodynamics. Yeah. Good. Both right. I don't know. I was trying to put the chapters together. I do the same thing all the time. I like try to they might be interested in that if I tie it all together. Talk about how sunlight becomes my corn tortilla. But then what I should really know is that it's not. My kids will be like, so like, they'll ask me some question like that. So like, where does what kind of energy is in chips? Oh, well, as soon as I do that, oh, well, no, never mind. No, I'm good. I'm like, seriously, you don't want to know? I'll look it up. I'm gonna watch a YouTube video, do it in like a minute and a half. All right. Sit there and listen to some old dude draw arrows on the board. Ridiculous. But for maybe one of you, maybe it clicks. So that's photosynthesis. Just want to make sure that I don't have like something else that I want to. No. Oh yeah, there's one more thing. Sort of about this. I need to put the Calvin cycle back up. So if you look at the Calvin cycle, if this comes up on the board again, you're going to notice that it's using more, I got to think about this, more ATP than electrons. So we've got like these two sources of energy. You've got like two buckets full of energy. One bucket has ATP in it, one bucket has electrons. You're using ATP twice here, and you've got like the electrons once. So eventually what happens is that like your ATP bucket gets empty, but you still got some electrons left in the other bucket. So you don't need more electrons. You need to go figure out how to get more just ATP by itself. So that's what happens when you run this machine for so long. you use up all your ATP, but you still got some of this left. So the plant has a way to go back in and just get ATP. So it involves hairy back. I call him hairy back because he doesn't wear a tank top. So hairy back is going to take some electrons. He's not going to put it in the bucket. He's going to drop it. He's going to throw it down. He's going to tell her, hold off for a minute. So photosystem 2, relax, take a break. Don't do anything. He's going to throw this down the ramp, make more ATP. Goes into photosystem 1. The sun hits it again, bounces back up and is caught. He's going to throw it down again. And it just keeps going like this in a cycle. So they call it cyclic electron flow. So the plant will do this sometimes, just kind of alter alter the light reactions. And it does it when it wants more ATP. So they call it cyclic, meaning like it's in a cycle. It used to be called cyclic photophosphorylation. So good thing they changed the name. Cyclic electron flow. No photosystem 2 is needed. Just make ATP. We're not trying to get extra electrons.
If we write down in like at some point because of hairy back, can we get bonus points?
Yeah. Absolutely.
Okay. From hairy back.
I had named for all of them at one time.
It's free bonus points.
Yeah, just right after hairy back, you're like bonus. I'm like writing because I'll forget. All right, that was the last thing. Now I have kind of a dilemma. Do I want to press on or do I want to just stop? Yeah, I know your answer. Let me stop recording.
Yeah, we did.
Yeah, we're gonna take a well. It is. It's time for.